So we're on lesson 5 and we're spending a bit of time today looking at the graphing calculator. So you're going to listen to this lesson, take notes as best you can, and then we'll make sure we practice a couple together in class. So for this problem, a hose sprays a stream of water across a lawn. The table shows the approximate height of the stream above the lawn at various differences from the person holding the nozzle. Write an algebraic model in vertex form that relates the height of the water to the distance from the person. So this is real life data, for sure, and you know your numbers aren't going to be perfect. So the first thing that we're going to do is to create a graph. So I need to decide first of all which is my independent and which is my dependent variable. So the height above the lawn depends on how far away the person is from the nozzle. So the height would depend on how far you are from the nozzle. So this is the independent. It's easier when you have time to get that figured out, but dependent. So this is the x values, this is the y values in conventional math form. So we want to graph this data. We want to have distance from the nozzle across the x-axis. So distance from nozzle, and this is in meters. So as I construct my graph, I'm thinking about the domain and the range. So I don't need negative values, so I can put my axis right in the left hand corner. So you could use a ruler, just saying. I'm going to use my drawing tool, and we're going to have distance. There we are. There. And then my y-axis will be up that way. Okay. I want to be able to go from 0 to 8. So I'm going to just count my squares and make sure that I do it in a nice even sort of a way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I don't quite have 16 squares. So I'm going to do 0, 1, 2, 3, 4, 5, 6, 7, 8. I can't skip squares because I don't quite have enough. Right. On the y-axis, I have height above the lawn. The funny part is I can't actually see my hand writing because it's in the way of the light. Okay, height above the lawn, also in meters. And I want to go from a value of 0 up to my highest value is 3. So I can skip quite a few here. 1, 2. You could have probably gone every 4th square, really. So I take some consideration to my domain and my range as I set up my graph, and I'm going to plot the points. We don't join the points, we just plot them. So my first point is 0, 0.5. So approximately right there. 1, 1.4. So we're eyeballing the best we can. If you can plot them as well, please. 2, 2.1. 3, 2.6, and 4, 2.9, 5, 3, 6, 2.9. Interesting. We're seeing a repeat pattern here. 7, 2.5. So a little bit different. And 8, 1.9. Okay, so we've plotted our points. And then we're going to ask you to come up with 2 equations of parabolas that might fit that data. So the first one asks us to create an algebraic model. Algebraic just means it has letters and numbers in it by hand in vertex form. So we know what vertex form looks like. Y equals A, x subtract h squared plus k. So we are fairly convinced by the table that we have found the largest value, and it seems to be the vertex because it goes down to the same value both to the left and to the right, which is what a parabola normally does. So I'm fairly convinced that the point 5, 3 is my vertex. So h and k would give me that vertex, so I want x subtract 5 and plus 3 at the end. If I want to find that exact a value, I need to substitute a point. I've got a lot of points to choose from. I want to choose the nicest. So of all the points I see, you know what, they're all about the same, but I think I'm going to do that one. So I'm going to substitute 0, 0.5. If you had chosen a different point, you might get a slightly different equation than I do, because we're talking about real life data. Everything's just a little bit off of perfect, as we like in mathematical world. Okay, so for a point, when I substitute, the point is always the x and y coordinates of a specific place. So I am going to put the 0.5 where the y is. I'm trying to solve for a. Put a 0 where the x is, and then I have some tidy up to do. So I am going to figure out my bracket and then square it, and then we'll worry about solving for a. So 0 subtract 5 is negative 5, and negative 5 squared is 25. So a times 25 plus 3 equals 0.5. At this point, I've done all the tidying that I can really, and I want to solve for a. So I'm undoing the layers and getting rid of this plus 3 first. I do that by subtracting 3 from both sides so that I am left with a times 25 equals negative 2.5. To get rid of a multiplication, because a squished up to 25 implies multiplication, I would divide both sides by 25. I end up with a equals negative 2.5 over 25. It is 0.1 or 1/10. Okay. Does it make sense that we have a negative a value? Yes, it opens upside down, so it does. Fairly wide parabola. So final answer, y equals negative 0.1 x subtract 5 squared plus 3. Then it asks us to create another algebraic model, but this time using the graphing calculator. So this is where you can just take some notes of the process before you use the calculator tomorrow. So we want to type this data into the graphing calculator so that it can create the equation for us. So anytime you're working with data, you want to be working in these buttons here that talk about statistics. Okay, so we're going to hit Stat, and Edit is the first option. Sorry, it's hard to get all of this in. Stat, and then Edit is your first option at the top. Edit, I'm going to hit Enter, and that gets you to your lists of data. So under, let's write that down, sorry. It doesn't like to let me write and look at a graphing calculator at the same time, so it might look a little funny. So Stat, Edit, Enter. Under L1 and L2, we enter our x and y values. So for this particular data, our x values are 0, 1, 2, 3, and all the way down to 8. You enter that data one at a time and hit Enter after each value. Then we scroll to the right and we're ready to enter the L2 data, which is our height above the lawn data. So we have 0.5, 1.4, and so on there. And I'll just enter that. More data. And you need to check that you've got the same number of pieces of data in both columns. If you have one piece missing, it's going to squawk at you. Okay, so we've got all of our data entered. The next thing that we need to do is to make sure that it is ready to graph our data. So up above the y equals button, which is all your graphing options along here, up above the y equals button it says stat plot. We want to be there and turn the statistics plotter on. So second function y equals is stat plot. The first option, I'm going to hit enter. And when I get there, I make sure it's on. Right now it's off. So I'm going to hit enter on the on. We're good to go. It should plot my data. If you hit graph right now, you might see it. You might have to fix your windows. So let's hit graph. Let's hit graph and mean it. There we go. There. We can see most of our data. So we can get this graphing calculator now to figure out the equation for us. Let's just make a little note here on your sheet that we need to do second function y equals stat plot on. And you may need to adjust your windows. We did not have to. But it's the same thinking that you did to set up your graph. What numbers would make sense for my x values and for my y values. All right, here it gets interesting. We're going to get the graphing calculator to give us the equation of the curve that goes through those points. So since it's dealing with numbers and statistics, a lot of data, we're going to go back to that stat button. Across the top, you see the option calc. So we go to stat button, option calc. That means it's going to calculate something for you. Scroll to the right, calc. I'm going to tell it, this is a quadratic. I am sure is a quadratic. You can see option number 5 is a quadratic. It says quadratic regression or quadrig. Option number 5. Quadratic regression. All right. Your screen will have the word quadrig. Well, it's not really a word, kind of a combination of words. And what you want it to look like is quadrig L1, comma, L2, comma, Y1. So L1 and L2 are up above the numbers 1 and 2. So to get this one, it would be second function number 1 button. Second function number 1. Then there's a comma button. Second function number 2. Then there's a comma button. And then to get Y1, it's crazy. If you're using Desmos today, it has its own way of typing this in. And you are free to use Desmos. That is not a problem at all. To get a variable there, or to tell it to type it into our grapher so that it will graph a curve through your points, you want to go to the vars button, which is for variables. Vars. It is right underneath the up arrow, down arrow button. You want specifically a y variable. So I'm going to scroll to the right, y bars. I want it to be a function. And your first option is Y1, so hit enter. Now that you've got it looking the way you want, you hit enter one more time. And there is our equation. So I am going to use 3 decimal places. Y equals negative decimal 1068. I just did 4, didn't I? Let's do 107. X squared plus 1.036 x plus 0.476. Rather different looking than the equation that we came up with. Here are our two models, and it says, compare your two models. How do they fit the graph? How do the algebraic models compare? How do they fit the data in the table? Which is your choice? Well, let's have a look at the graphing calculator, and we'll put both of those equations in and see what we think, which one fits the data a little bit better. It's a good idea to plot these things together to be able to accurately compare them. So once we've got our equation like we did on the last slide, it will be stored under the y equals button, and it is stored with all the glorious decimals. So that second equation is fully stored already in the calculator. I'm going to go down and type the one that we created algebraically as my y2. So I'm kind of changing the order here, but that's okay. My second one was negative 0.1 bracket x subtract 5 squared plus 3. So our graph, there's the one that the calculator did for us, fits right through the middle of the data, and the second one doesn't look a whole lot different, does it? Let's change our windows for a second so that we can see a little bit more. Negative 3 to 10, and we want to go just a little bit lower. No. Okay. There's our dots. There's the calculator's curve, and here's ours coming right along. Ours was a little bit higher over here, but not a lot different other than that. They shadow each other pretty closely. So the questions ask us, how do they fit the graph? Well, they both fit the graph very, very well. The calculator went right through the middle, and ours maybe lies a little bit on top of the data. And it says, how do they compare? Well, both accurately fit the data, and which is your choice? It depends what you're wanting to do. Do you feel that one is more accurate than the other? That would be a real important point of discussion. And is one easier to manipulate or easier to use to solve problems? Well, this one fit very well. That data wasn't bad data. It all fit fairly closely to the shape of a parabola. I think they're both quite accurate, but the calculator might be a little bit more accurate. Sometimes it's remarkably better. If we were trying to solve any problems with this, I would find the second equation scary. But the first one might be easier to manipulate, is the one that we did by hand. If I needed to know the vertex, for instance, there it is. If I needed to find an x-intercept, perhaps the second one I could use the quadratic formula. I don't know. We have judgment calls to make about data and which equation would be better to use depending on accuracy and how easily we want to determine answers. This would not be a nice equation to do in x-intercept form. First of all, completing the square with the second one would make me cry, and the data did not give us nice x-intercepts to work with. If we could get it in factored form, we could find x-intercepts more easily, but it would not be easy to determine at this point.